Alright, so we have two randomized algorithms. One gives us a 1 over 2 approximation, that's the randomized algorithm, and the second one gives us a 1 minus 1 over e approximation. That's the randomized LP rounding algorithm. Both are randomized, but we can de-randomize both of them, so we have a deterministic algorithm. Now if I take the better of them, what does that give me? Of course, the better one is the second one, so it gives me a 1 minus 1 over e approximation. And in general, that's the best we can do. If we have two algorithms, and both have different approximation factors, and we take the better one, then that in general is just the approximation of the better algorithm. But the interesting thing is that here, whenever one algorithm performs badly, that the other one performs very well. And if we just take the better one, then that even improves our approximation factor. Then we even get a 3 over 4 approximation for MaxSat. And to prove that, that's again very interesting, we can also use a probabilistic argument. We don't choose the better one, but with probability 50% we choose the first algorithm, and with probability 50% the second algorithm. And even for that random choice, we can already show that that gives us a 3 over 4 approximation. That means if I take the better one, then that cannot be worse than if I take a random one. So the better solution has to be at least as good as the expectation of this random choice. Let's try to prove this. The probability that a clause is satisfied in this algorithm that randomly chooses one of the randomized algorithms is at least the mean of the probability that it is satisfied in these algorithms. So it is at least 1 over 2 times the probability it's satisfied in the LP rounding algorithm plus the probability that it's satisfied in the randomized algorithm. And now note that this set J star that we get from the LP relaxation, this is somewhere between 0 and 1. And since we want to show at least, we can just pull it out and put it here. And the whole thing will only get smaller. Now we want to show that this here, this term, is at least 3 over 4 times set J star. And for that, let's first consider the case that Lj is 1. So we have a clause with exactly one variable, one literal. What happens here? This one becomes a 1, so this is a 0, so here we have a 1. This here is a 1/2, so this becomes 1/2, that means we have here 1.5, divided by 2, we have 3 divided by 4 times set J star. So we get exactly this bound. What if Lj is 2? This here becomes a 2, so we have 1 over 2. To the power of 2 is 1 over 4, so this here is 3 over 4. And here, 1 minus 2 to the minus 2 is 1 minus 1 over 4 is also 3 over 4. So both are 3 over 4, means their average is also 3 over 4 times set J star. We then have exactly the bound that we want. What if Lj is larger? If it's at least 3, then the first part we have here, we can use the same formula as we had before that shows that this is at least 1 minus 1 over e. And for the right one, if Lj is at least 3, then this is at most 1 over 8, so this whole thing is at least 7 over 8. And then if we take the arithmetic mean of these two, this was about 0.63, this is about 0.875, so the average is somewhere at 0.753, which is more than 3 over 4. So for every value of Lj, this gives us at least 3 over 4. And that means for every clause, the probability that it is satisfied is at least 3 over 4 times its assignment in the optimum of the LP relaxation. And then we can continue exactly as here. We have the probability that it is satisfied, which is 3 over 4 times set J star. So instead of 1 minus 1 over e, here we have a 3 over 4 and then we get a 3 over 4 times opt. So this whole algorithm gives us a 3 over 4 approximation. Before we conclude, I want to visualize the plots of these two approximation functions. We had two algorithms, and let's have a look at what is the probability that a clause is satisfied divided by the set trace star. For the first algorithm, we have at most 1 minus 1 over 2 to the Lj. So this goes up very quickly if we have clauses with many literals. For the LP rounding, we had 1 minus this term to the Lj. You can see this is large in the beginning, but then it goes down. So the first algorithm, the normal randomization, the coin flipping, is better for large values of Lj, where we have clauses with many literals. And the randomized LP rounding is better for small values, where we have clauses with very few literals. That means that I have a higher probability of satisfying a clause. Now I want to look at the mean of them. That looks like this. And the interesting thing is, it is not always at least 3 over 4. So in this whole part here, between 1 and 2, it is less than that. But since the number of literals is always integral, everything here doesn't matter. We only need the points at the integer coordinates. And that's exactly 0.75 at 1 at 2 and larger later. And actually, if we look at the maximum of those two, we will see that in the beginning it's 1, and it goes down to 0.75, and then it will go up again. So this is always at least 0.75. And clearly we can de-randomize this algorithm. I mean, we have already de-randomized both other algorithms, so for this one, it's just one more step. Pick the better of the two, and you're done. And that's all I wanted to show you today about maximum satisfiability and randomized approximation algorithms. Thank you for watching.